In lecture number 26, we first talked about the temperature dependence of carrier mobility and electrical conductivity. We then talked about degenerate doping, and then we finished off by talking about the dynamics of carriers in semiconductors with regard to generation and recombination of these carriers. So the first learning outcome is that you should be able to describe the qualitative and quantitative temperature dependencies of the carrier mobility and electrical conductivity. For carrier mobility, we have two different temperature ranges. In the high temperature range, we have lattice vibration scattering, limiting the carrier mobility. You can also call it phonon scattering. That gives you a T to the minus 3½ dependence for the mobility. In the low temperature range, the mobility is limited by ionizing impurity scattering. That gives you T to the 3½ dependence for the mobility. You can combine these two scattering mechanisms using the Mathiassen's root to get the overall mobility. Now, both mechanisms are present when we talk about the electron mobility in metals, but at that time, the temperature functional dependencies are a little bit different. In the high temperature range, we have a linearly increasing resistivity. That basically the mobility goes down by 1/T in the high temperature range. In the low temperature range, the ionizing impurity scattering term is mostly temperature independent. And that difference is mostly caused by the difference in the kinetic energy or the average velocity in these systems at different temperatures. In semiconductors, we know that average kinetic energy of electrons is only 3½ kT, and that gives you a very low velocity, and that's also temperature dependent. In the case of metals, the thermal velocity of electrons is related to the Fermi energy, which is much, much higher, several eV, and also temperature independent. By combining the temperature dependencies of the carrier concentration and mobility, you can get the temperature dependence of the conductivity. So for the carrier concentration, we have intrinsic, we have the saturation, and we have ionization range. And for the mobility, we have lattice scattering at high temperature and ionizing impurity scattering at low temperature. So by combining these two functional dependencies, you can get also the conductivity as a function of temperature in both the intrinsic and ionization, in which cases the carrier concentration change at different temperatures will dominate the relatively weak temperature dependence of the mobility. But in the saturation range, as the carrier concentration stays the same, the relatively weak mobility, temperature dependence of the mobility will show up as a little hump in some way in the middle. We also need to pay attention to the relative magnitude and overall trend of the semiconductor resistivity compared with metal. Metal has low resistivity, and the resistivity generally increases with temperature. But for semiconductors, the resistivity is a lot higher since we have very low carrier concentrations, and also in general, the resistivity decreases other than the little hump area regarding to the saturation range. The next student outcome is that you should be able to explain the consequences of degenerate doping on carrier concentrations and Fermi level locations. So we have all these equations relating the carrier concentrations to the Fermi level position inside the band gap. And at the time, we apply some assumptions. And the assumption is that the doping concentrations will not be very high. The electron concentration will not be much higher than, higher than the defect the electron concentration is much smaller than the effective density of states in the conduction band. Hole concentration will be much smaller than effective density of states in the valence band. They also says that the probability for electrons occupying the conduction band states and for the holes to occupy valence band states is going to be much smaller than 1. Equivalently, it says that the Fermi level is going to be at least several kT below the conduction band edge, or at least several kT above the valence band edge. So these are the relatively low doping situations. But if you do have a very high doping concentration, such that you get to close to NCOMV or even greater than those, then we can no longer apply those equations to relate the carrier concentration to the Fermi level locations. In that case, actually, the carrier concentration can be so high such that the Fermi energy may be very close to the conduction of valence band edges, or maybe even go into the bands, such that now the lowest states in the conduction band or the highest states in the valence band will be occupied by electrons or holes with a probability greater than 50%. This is a so-called degenerate doping situation. And later on, as we talk about, it'll be utilized in many different situations. Next student learning outcome is to describe the various charge generation and recombination processes in semiconductors. So we have generation and recombination due to the thermal environment that we have. So that basically that gives you a dynamic balance between the generation and recombination that gets you N times P product being Ni squared. That this on a thermal equilibrium situation. Electron going up, that probability is not very high, and just because KT is typically much smaller than the band gap, but when these carriers do recombine, the energy is given up into the heat and goes back to the thermal environment. There are other ways of generating carriers, for example, photo generation. Obviously, in that case, the photon energy needs to be at least the band gap to satisfy the energy conservation. But then these carriers can also recombine. They can recombine and then re-emit as in the form of a photon. This is a band-to-band recombination. And anytime you have, let's for example, photo generation or other kind of generation processes to create excess carriers, then the recombination process will dominate and then tend to reduce the carrier concentration over a long time. But on the other hand, if somehow you have carrier deficiency, so that the carrier concentration product is less than Ni squared, then the generation will tend to increase the carrier concentration to the equilibrium level. There's also a difference between direct and indirect recombination. Direct means that just electron and hole in electron in the conduction band, a hole in the valence band can recombine directly, or the recombination can take place via some so-called recombination centers or defect states. And so, for example, electron can be first goes to these recombination center level, and then recombination center, and then holes moving by can recombine with that electron. And in both direct and indirect recombination cases, we can have so-called radiative recombination. Basically, the energy through the recombination will be given out in the form of a photon. Basically, light is emitted. Or it can be non-radiative recombination, and the energy will be going out as in the form of a heat, basically phonons in the system. So the last student learning outcome is to describe what is minority carrier lifetime and how it is related to the excess carrier concentrations. So if we do have for example, photo generation to create excess carriers, same amount of electrons and same amount of holes, excess carrier concentration, and then if we suddenly take away the illumination, then these excess carriers will actually be removed due to the recombination process. In this case, if we assume some low-level injections, that means the excess carrier concentration is not large enough to distort the majority carrier concentration, but it is significant enough to distort the minority carrier concentration. So in that case, we only need to focus on the minority carriers and then look at its rate of change over time. And this rate of change can be written in two parts. One is the rate of change induced by the photo generation. That's a bit positive term. And then once we have excess carriers, then the recombination will tend to take it away. And so that process obviously can is a process that will reduce carriers. So there's a negative term in front, and then it can be described as sort of proportional to the overall excess carrier concentration you have. And there's a lifetime. This is called minority carrier lifetime. And so that gives you sort of a transient behavior when you just turn on or turn off the light generation. So you're going to have a transient process, which is described by this exponential term, and this time constant is this minority carrier lifetime. So that gives you a gradual increase or gradual decrease to the steady state situation. This is the end of the review.